So far we have seen conflict serializability and view serializability, but the problem with them is implementation. Example, you have some schedule, complete schedule, then we can easily check whether it is conflict serializable or not. But in reality, you can't have a schedule completely, right? So example, you have some set of transaction T1, T2, T3, and at any point of view, at any point of time, if you see only partial list of instructions you can see, because they are still getting executed. So that's why at any point of time in real time, so all the transactions with the complete list of their operations might not be available. So we cannot apply conflict serializability or view serializability readily. So that's why that conflict serializability and view serializability we use as theoretical foundations and benchmarks. So they are actually, I can say good algorithms for finding whether a transaction, a set of transactions and their interleaving is good or bad, correct? So what we are going to do is then we are going to implement protocols. So example, let's say if we create a protocol P1, then we are going to compare this with conflict serializability, otherwise view serializability. We say like this is a protocol. We'll ask Mr. Protocol how many schedules you are able to allow. Mr. Conflict serializability, how many schedules you can allow. So we compare like who is good, who is bad. Like at least our final target is your protocol, whatever you design, that should be able to somehow filter the schedules. Otherwise, should be able to find out good schedules like as good as conflict serializable. Otherwise, as good as view serializability. Understand? So this conflict serializability and view serializability has some capacity. That means somehow they are going to find out good and bad. Similarly, your protocols also should find out good and bad. At least they should do as good as conflict serializability. Understand? We will see, of course, we are going to compare our protocols with conflict serializability and view serializability. Before that, first of all, we'll try to understand existing protocols. What are the protocols we have is, we have basically two important protocols. One is locking protocol, second one timestamp based protocols. We will see one by one. Let's begin with locking protocols. Okay, now we'll see locking protocols. So we'll see how these efficient protocols got proposed. Before that, we start with basic idea, like so that you can understand that efficient models. So first one is actually, what if we have only one lock? And what is this lock first of all? And how this is going to control your transaction concurrency is the question, right? Example, when you have a transaction and it is going to issue an operation called read of A, then your DBMS is going to lock your database item A, and after that it is going to unlock the database item A. First of all, what is lock, sir? Locking is nothing but it's a binary variable. Let's say for every database variable you assume that there is a lock A. That means there is a variable called lock. So this lock can be imagined as a variable and it can take either 0 or 1. 0 means unlocked, 1 means locked. Now whenever this lock is 1, that means it is used by someone. If this is 0, that means at least at this moment it is free. In that way lock can be understood. Now you have such lock. So what are you going to do? For every database variable there is a lock. Then whenever transaction T1 wants to do read of A, on behalf of T1, your DBMS software first of all will try to execute lock instruction, lock A. After that it will try to execute unlock of A. These two things it will do. If this lock of A is successful, then read of A can be done. Otherwise read of A cannot be done. If lock of A is successful, read of A will be done and unlock of A will be done. That means again your lock will be released. So what is the meaning of releasing the lock? I will tell you. So lock of A is a binary variable, right? Initially when no one acquires this lock on A, it will be 0. Now at this moment really lock of A is executed for on behalf of transaction 1, then this will be made 1. So that means no one can try this, no one can access database variable A. After that read of A will be performed, then unlock of A will make this again 0 so that others can again use that variable A. That is the idea. In that way, at a time, only one person can access database variable item A. In that way, we are trying. Okay. So somehow we are hoping that we can control the concurrency. We will see how these kind of mechanisms are going to control the concurrency. First, understand the basic elements of these locking protocols, that is lock. So this basic lock generally has some problems. What are they? I will tell you. One is, if you have only one model of lock, what happens? I will tell you. Consider the scenario. There are two transactions and they want to read a database item A at a time, like this, read of A, read of A. Now, and assume that for some reasons you did not unlock it. Imagine this situation. Otherwise, almost at a time, same time, transaction T2 wants to read parallelly. Then at this moment I can say that T1 is having the lock, correct? So what is our idea? Whenever some transaction acquires a lock on some variable A, we can't give that lock to others. Then T2 transaction, if it will try lock of A, then it will be unsuccessful. Now let me ask the question. Why it is unsuccessful? Because already lock variable is 1. When lock variable is 1, we cannot give to others. That is what initial model. So by this time, whoever attending my lectures are slowly understanding, this is awkward model. Yes, read and read. Multiple people at a time can access the database item A and they can read it. What is the big deal on that, correct? But this locking mechanism, what you are using at this moment, what is our goal? If lock is 1, then others cannot access the variable A, right? That is what the model we are working out. So that model now will not work. For that, what we do is, so this is not good idea. Unnecessarily we are restricting ourselves and we are accessing, otherwise we are permitting only limited concurrency. How to increase the concurrency? How to allow multiple transactions who are readers? For that, this locking mechanism should be improvised. That's why slowly people introduced two different kinds of locks. One is shared lock, second one exclusive lock. From now onwards, I use X symbol for exclusive lock and S for shared lock. So shared lock and exclusive lock. The purpose of shared lock is, whenever a transaction issues only read operation, then shared lock will be issued. Now whenever a transaction has read followed by write, otherwise write. So that means finally, whenever a transaction wants to write the database item A, then we are going to issue exclusive lock. Understand? So this is the idea. Now we'll try to figure it out. So whenever you have two different locks, different models of locks, shared and exclusive, we have to understand and we have to focus on this compatibility matrix. That means every DBMS should aware of this compatibility matrix. What is that is? Example, there is a shared lock already issued by someone, then others can issue shared lock or not is the question that will be answered by this compatibility matrix. So here X and here X. So DBMS maintains this compatibility matrix. So shared, that means already transaction T1 holds a shared lock. Imagine this situation. There is a transaction T1. So whatever may be the reason, now currently it is acquiring a lock in a dash mode, shared mode. On which variable? Let's say some variable A. Okay, see this situation. Then the question, transaction T2 can acquire shared lock or not? That is shared. Yes. Multiple people can acquire shared lock. That's why we created two different locks. So shared and shared is okay. That means multiple people are going to acquire same lock, which is shared lock on same database item A, and we allow it so that we can increase the concurrency. Second one, if someone already T1 holds shared lock, T2 asks exclusive lock, then we should not allow, right? This X means not possible. Let's write like this. Wrong. So DBMS will not allow it. Now T1 is holding exclusive lock and T2 wants shared lock on it. Is it allowed? Not allowed. Now similarly exclusive also not allowed. This is called compatibility matrix for shared locks and exclusive locks. So we remember it. Otherwise that is DBMS responsibility actually. So DBMS will remember it. Now how these locks your DBMS is going to use and how this transactions are going to be controlled by your DBMS, we will see. So you should remember one important point, that is DBMS is going to maintain all these locks, and what this locks will be doing, we will see. First of all, take one small problem. Let's say there are two transactions. They wants to do this thing. One transaction wants to do read of A, second one write of A. So how your DBMS is going to perform these operations, we'll see using locking mechanism. So we assume that there is a variable called lock of A, okay, because we have only one variable now for simplicity. This is lock of a variable. So for this lock of a variable, it is a binary variable, it will have either 0 or 1, right? So now whenever T1 issues read of A, on behalf of T1, your DBMS will place an instruction called shared lock of A, since it is a read operation. Okay, so first of all, it will keep this shade of A and it will try to execute it, try to achieve it. Okay, so it will come to lock of A. Your DBMS is going to do all this stuff. Okay, so lock of A. Initially, it will be 0. So it will see that. So that means this lock is not, that means variable A doesn't have any lock. So immediately it will be granted, then it will be made 1. Already I told you. So here we have two different locks, shared and exclusive. Shared has different functionality and exclusive has different functionality. Then we should have one more extra component, that is mode. So we assume that every lock has, locking thing, like that means we can lock it and unlock it. At the same time we can remember the mode. So on which mode you are locking it? Shared. So here we will have a bit. For readability purpose, I am using text, but generally it will be a bit like 0 or 1. Okay, so we use shared mode, right? So I am just giving you data structures in high level. Later we can convert them to low level data structures, not a problem, correct? Now second one, after that at 10 o'clock read of A will be done. Now see, transaction T1's read of A is performed. After that immediately your DBMS will unlock it because the desired operation has been done, right? So let's say DBMS releases it. So now whenever this unlock of A is done, what DBMS will do, we'll see. Whenever this unlock of A is issued by your DBMS, on behalf of that your DBMS will come to lock of A, that means variable A's lock, and it will make it 0 again, and this mode will be removed. Understand? So this is about transaction T1's unlock. After that, let's say 11 o'clock, let's say there is an operation write of A. Then transaction T2 is going to again it wants to perform write of A. Before that DBMS will keep exclusive lock, correct? So exclusive lock, and it will try to acquire it, it will try to achieve it. Let's see whether it achieves or not. It's quite obvious because when you go to here, lock is 0, then we'll make it 1 and mode is exclusive lock, correct? Then we will perform. So so far it's working, right? But we will see one more complex idea. If you have this kind of transactions T1 and T2, and T1 has, let's say, read of A and T2 has write of A, but almost same time, so that still you did not release it. So somehow for some reason, because you did not get, assume that let's say you are, these two transactions are going to be executed under same system, so that when T2 is getting executed, T1 cannot get executed. That's the reason. First of all, successfully we achieved shared lock. Yes, I put right mark, that means we achieved it, and read of A is done. Then suddenly what happened, context switching is done. You will understand this after learning operating systems. So after context switching, what happened? So T2 got chance to be executed under CPU. Then here your DBMS will do what? First of all, it will try to achieve exclusive lock on A. So we'll see at this moment, what is this? Your lock is, your variable A is locked under shared mode, correct? Now, so on behalf of this instruction, your DBMS first of all will come here and it will check. It is already locked. Which mode? Shared mode. But then X versus, now the compatibility matrix will be evaluated. X versus S, no permission. So here finally this will be rejected. That means what is rejected? That means exclusive lock is unsuccessful. Now the question here is, what DBMS will do? What is the action it will perform? There are two possibilities. One thing is seriously writing some code such a way that that code will ping. That means again it's a DBMS software. So DBMS, some code will be embedded here such a way that whenever that code is executed, so this lock will be pinged like this. That means it will be, because now it is, your variable is busy, right? So DBMS can add some extra code. That code is such a way that whenever that code is executed by your transaction on behalf of your transaction, so this lock should be pinged. That means like this, Mr. Lock, are you available? Mr. Lock, are you available? It's a loop. So there will be a loop. Understand? So is it good to write a loop? Generally in programming perspective, you will be learning it after learning operating system. This is called busy waiting. Now your transaction is busily waiting for this loop should be terminated, correct? Then only will come to write of A. But this loop will be terminated only when this lock is 0, correct? So whenever this lock is 1, it will be seriously pinging like this, correct? Now what I want to say is, so this unnecessarily you are wasting computer resources, because when to execute this loop, your computer should be busy, right? Your processor will be busy. That's why no one generally will implement this kind of model. There is another model. What is that? Is your locking will be implemented. So this is not part of your transaction code. It is executed by your DBMS, and the code is also part of DBMS. What is that code? I will tell you. The functionality of that code is, whenever exclusive lock of A is unsuccessful, then your DBMS will execute code. That code will do this one. What is that? Is so for every lock there will be some blocked transactions. Understand? So here this your DBMS will maintain some set of blocked transactions on behalf of every variable. See here, example, exclusive lock on A, right? So who issued it? On behalf of whom we issued it? T2, right? T2 will be automatically blocked. When T2 is blocked, then T2 cannot be released. That means we never execute T2 until something miracle happens. I will tell you what is that miracle. So slowly what happens is, assume that in the system there are only 2 transactions, then eventually so transaction T1 will release, T1 will get turned first of all. Whenever T1 gets turned, then your DBMS will issue unlock of A on behalf of T1, and it will try to achieve it. So how unlock of A will be performed by your DBMS, I will tell you. So here I would like to stop and I will tell you one point. This shared lock of A, exclusive lock of A, unlock of A, these are all instructions which are executed by your DBMS and which are initiated by your DBMS. They are placed by your DBMS, remember it. So whenever unlock of A is placed by your DBMS and executed, what happens is, immediately this A will be made 0, such a way code is written. Now mode will be cancelled, otherwise you can keep any mode, doesn't matter, because lock is free. Now immediately this T2 will be released. When T2 is released, then it will come back again, it will try to issue. That means 9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock, 1 o'clock. Try to understand. But 11 o'clock instruction was unsuccessful, so 12 o'clock instruction was not done. Then at 1 o'clock when unlocking is done, then at 2 o'clock this, let's say, transaction T2 is released, then T2 will try to issue again write of A, because it is not done, right? So T2 will come and it will try to do write of A again, but before that again your DBMS will try to achieve exclusive lock of A. Same story, but rather than here we are doing it again at 2 o'clock. So that means this set of instructions has been postponed. So in that way we are ensuring the concurrency. Understand? So slowly we moved this instruction to 2 o'clock. Now we'll try one more time. This time exclusive lock on A. Then DBMS will come to lock and it will check whether it is available or not. Yes, available, make it 1, and mode is what? Exclusive, and we continue this process. Meanwhile, if there is any other transaction, if that transaction wants to achieve any lock on this database item, immediately they will be blocked, like T2 got blocked. Understand? This is the way this kind of locking mechanisms works. Slowly we are understanding how locking works, right? So don't worry. So we'll slowly understand the efficient algorithms. Before that, we'll see basic model. I'm slowly teaching you the stuff related to locking. Understand? Now we'll see the schedule and we try to achieve the locks. Okay. So I'm going to teach you one potential problem with our basic model. So after that we improve it. So the basic problem is here. Example, let's say transaction T1 want to do read of A. So at that time, so your DBMS will try to issue shared lock, right? Whether it is successful or not, we'll see. Since initially available will be 0, then we made it 1 and it is successful now. Mode is now shared mode and counter is 1. Counter is going to indicate the number of transactions which are holding the lock at this moment 1. Initially it is 0. Now no blocked transactions. I assume that, let's say, you have one computer which is executing all the transactions. So we don't know, it depends on the operating system which transaction gets turned. So at this moment, let's say, what if T2 gets turned while still T1 is proceeding? That means T1 is doing read of A. It was not completed. Meanwhile, let's say T2 gets chance. What happens? Then DBMS will try to execute exclusive lock on A on behalf of T2. So I'm talking about one possibility. So on that possibility, so your DBMS will come to A and it will see availability. Since it is 1 and this mode is shared lock, that means exclusive versus shared, not compatible. Immediately your such transaction will be blocked. When it will be released is when this lock will become free. We'll see that. So meanwhile, so now I can say that this is not finally executed, right? So what we do is after some time we assume that, let's say T3 gets chance. If T3 gets chance, what happens? So here it is read of A, right? So DBMS will again try to achieve shared lock on A. Yes. So DBMS will come here, availability 1, no problem, but at least compatibility important. Shared versus shared, right? Shared versus shared is possible. That's why we make counter to 2. Understand? So after that, I assume that again, let's say T2 gets turned. T2 never gets turned because T2 got blocked, right? So until someone releases it, it never gets chance. That means T2 is not at all active process in the computer. So OS never schedule it. Understand? Now we will see what happens. After that, when time proceeds, so T4 gets chance. Okay. So when T4 gets chance, before that we assume that, let's say T1 got chance, because T1 was not completely executed its instructions, right? What if T1 gets chance? Then let's say T1 completed its read completely, and then after that your DBMS is going to do unlock of A here, somewhere here. So I don't want to write here because it was not done immediately, correct? Somewhere here unlocking is done. So if unlocking is done, how this unlocking is performed by your DBMS will see. So availability, this you should not make it 0 because there are some other transactions which are holding the lock. So what we have to do is, first of all we have to make counter to 1. Yes, done. That means still one transaction is holding the lock. So don't make avail to 0. So still mode is don't disturb the mode also. So that is not our responsibility now. But don't release T2 also because still there is one transaction which is holding the I can say conflicting lock. Then what happens is, let's say what if T4 gets turned? So anyone can get the turn now, right? If T4 gets turned and it says that I am read operation, so I am compatible. So DBMS will try to achieve shared lock and DBMS will realize that shared versus shared, okay, and counter will become 2. See, what I want to tell you is still T2 is blocked. It will not be released until this availability is 0. But when it will be 0, if all the transactions which are holding the lock releases it. But so far T1 released it, but T2 and T3 and T4 have not released it, correct? Now in between what can happen is, so what if T2 releases it? Be positive and think that, let's say T2 releases it. When T2 releases it, I'm just telling one possibility. Don't ask me why are you doing in that way. So this is one of the possibility where T2 may be blocked for a long time. That's what we are trying. So here counter will become 1 since who is unlocking it? T3. So DBMS executes unlock and availability will be still 1 because there is one transaction, correct? So then later see the situation. What if T5 comes and T5 issues read of A? Your DBMS will try to achieve it. And my assumption is, let's say this is now T5's turn. T5 got turned into processor. That means processor is currently executing T5. Then what happens? Again this will be successful. Counter will become 2. So what I want to say finally is, when T2 is one writer and there are multiple readers, that multiple readers can indefinitely hold this lock and T2 may be indefinitely blocked, at least for long time. So this problem is called starvation. So why are you getting starvation problem? Because when there is one reader already holding the lock, then you are giving chance to other reader. So this situation might occur. So I can generalize it like, I can show a problem in a different way. So this is the right idea, but we'll try to understand the theory. There are 100 readers in the system. There is only one writer, just for exaggerating the things. That's it. I'm just exaggerating the things. So it's very rare to have 100 readers and one writer, but take this situation. There are 100 readers and one writer. Initially, one reader holds the lock on database item A. Okay, then whenever that writer tries, then he will be blocked. See, this is a writer. Now he will be put in jail, correct? Because he is trying to access, I mean, he's trying to achieve conflicting lock, right? So that's why he will be in jail. Then see the situation from now onwards. So this lock is released by someone and holding by someone. See, this 99 readers, other readers, they're coming like this initially. So number one, reader number one is, holding it. Then after that, so 2 comes and 1 leaves, 3 comes and 2 leaves. In that way, if someone comes and someone leaves, always so that such a way that, so this lock is always busy, we can manage it, right? And this writer never gets chance, correct? So this is called starvation. How to avoid the starvation? Simple. From now onwards, if there is a blocked transaction, so it will be given priority. That's why, so though there is a reader and lock is compatible, but what we do is we give chance to block a transaction. How that will be achieved, I will show you with this same example. Okay, now we'll see now same example, but this time a modification is, whenever a writer is blocked, then no reader is permitted though there is a compatibility. Okay, we'll see that. I will show with example. First time, let's say T1 gets chance, then your DBMS will issue shade lock on A and it will be successful and availability will become 1, mode is shade lock and counter is 1. Now no blocked transactions. After that, let's say T2 is also reader, then let's say T2 gets chance, but so far T1 has not released it. Okay, so let's say T2 gets chance, then on behalf of T2 your DBMS issues shade lock. So since now first of all we'll see block transactions. Is there any block transaction? No. Then immediately we will make counter to 1. That means counter to 2. That means we allow this also because there is no other person who is competing for it. So then availability 1, mode is still S and counter is 2. Then later what happens is, so one day T3 gets chance, right? So whenever T3 gets chance, then it will try to achieve exclusive lock on A, then we'll come here and availability is 1. At least first we'll see block transactions, no, right? But mode is shade lock, then it is not permitted. So your transaction T3 will be blocked. Now next, after some time, let's say just for one randomness, we assume that let's say T1 gets chance, and since T1's read of A is done, we assume like that, then so T1 releases the lock. When T1 releases the lock, then your DBMS will try to execute that unlock of A. So unlock of A it will try and counter will be made 1 and still mode is mode and availability is availability, but block transaction will not be removed. The reason still there is one element, otherwise one transaction still holding the lock. Then eventually now T4 gets chance, just possibility. If T4 gets chance, then you might ask this question, sir, what if T2 gets chance? If T2 gets chance, then T2 will release T3. But we are just trying a possibility where we can hold block T3 for a long time. That is not possible, I am saying. Why? We will see. If T4 gets chance, if T2 gets chance, then T3 will be released and it might acquire the lock. But we'll try this T4, that's why. If T4 gets chance, then it will try to achieve shade lock on A. In our new model, first of all we will see availability 1. Next we will go to block transactions. First of all we will see the mode. Yes, shade versus shade, okay, compatible. But we will not join this group. First of all we will see block transactions. Since there is one block transaction, then this T3, T4, though it is compatible, it will not be given lock. It will be blocked, and the mode also will be remembered, so if possible. So along with the transaction, what is the lock model it is trying? Shade. And sorry, this is T4, right? What is the lock model it was trying? Exclusive. Let's remember that, understand. Now after that, let's say eventually let's say T5 gets turned. If T5 gets turned, so it also will try to achieve shade lock on A. So DBMS will try it, and since there are already 2 block transactions, T5 also will be blocked. And what is the mode? So T5's mode is, sorry, T4's mode is shade, so a mistake, and T3's mode was exclusive. Here T5 also will be blocked and the mode is shade. So this is the way we maintain this data structure. Now you see, what I want to say is the other readers are now not getting the chance to lock it, so that T3 will not be indefinitely blocked and T3 is not getting now starvation problem. So after some time what happens, we assume that eventually at some time T2 will get turned and T2 will release the lock. Sir, what if T2 will doesn't release the lock? If T2 doesn't release the lock, then why you are thinking like that? Since T2 is a transaction, so first of all, T2 should get turn on a computer, right? So your processor is going to execute this transaction, then eventually it will release it because DBMS is going to take care of that. So whenever T2 gets chance, then once read is done, your database is going to keep an instruction called unlock. The only possibility is what if T2 never gets chance to getting executed, so that is not our problem. It is CPU scheduling algorithms problem, so that we don't bother, right? Operating system will take care of this thing. What is that? So these are all the programs under operating system, right? Every program is program under operating system, then operating system will take care of that kind of things. So we say that if that is the situation, we say that T2 is having starvation, but OS will take care of that things. So at this moment we assume that everyone gets fair share of CPU execution, then T2 gets chance at that time. So DBMS will execute unlock of A, then this counter will become 0, then all this T3, T4, T5 will be released. So everything, not only T3, because whenever this availability becomes 0, that means counter is 0, then availability will be made 0, then mode will be removed and all the transactions T3, T4, T5 will be released. Now whoever gets turned, so that transaction is going to be getting the chance. Example, let's say really this CPU scheduling is fair, then T3 gets chance again because T4 got chance, T5 got chance, right, under CPU. Then now let's say T3 gets again chance at that time. So T3 is going to make mode exclusive lock, counter 1 and availability to 1, and so this blocked thing, right? All blocked are released, now no blocked things, understand? So then T3 will complete its write operation. This is the way we are going to put shared locks and exclusive locks, and we are going to operate this data structure, understand? From now onwards I don't show that, directly I say that, so I acquire a lock, otherwise I release the lock, and this kind of functionality I don't show, but you can implicitly assume that, understand? So this is about locking mechanism, right? So from now onwards I follow this mechanism. Let's summarize it. What is that? Whenever a transaction wants to acquire a lock, if it is really available, and then it will be given, and if the lock is not available, that means lock is locked, that means already someone is acquiring the lock and the mode is shared lock and no block transaction is there, that means on behalf of lock A, so the mode is shared lock, that means someone achieved only shared lock, and you also want to do sharing, that means you want to achieve shared lock but no block transaction, then you will be given chance. Now second possibility, the lock mode is shared lock, already it is acquired by someone, but the mode is shared lock and you want exclusive lock, then you will not be given at any cost. Now the third possibility, the lock model is exclusive lock, someone is already holding exclusive lock, and though you are a reader, if you want shared lock or exclusive lock, nothing will be given, understand? Now only compatibility is like this. If availability is 1, that means someone is holding the lock and the mode is shared lock, and if you want shared lock, then it will be given in only one consideration, that is at that time the block transaction list should be empty, otherwise still this is also not given, shared and shared. Why it is, why we do like that? So that starvation will be reduced, otherwise writers will seriously face a problem of starvation, that we have seen. That's it. Okay, now we will see locking protocol. So far just we are seeing the locking mechanism, we are going to see locking protocols. Before that, some more things you should learn. So there is a concept called lock upgradation and lock downgradation. I will explain that. Let's see lock upgradation and lock downgradation. Example, see the situation, transaction T1 has some read operation followed by write operation, and assume that let's say at this moment that lock on A is free, then your DBMS, if it tries here shared lock of A, it will be successful, correct? Since we are going to do read operation, we will make it shared of A. So after some time you are having write of A. So because of that, So there are two options. One is release your lock and acquire a new lock called exclusive lock because it is writing, correct. Second one, we can go for lock upgradation. There are two possibilities. One possibility, you know that, simply release shared lock and go for new lock, that is exclusive lock. The second possibility, don't release it. Without releasing it, simply upgrade it. So change your lock model to shared lock to exclusive lock. So like this. So first of all we take shared lock. After that, whenever you see write operation, we will make it exclusive lock. So it is giving flexibility, right? So then we will release here. But for whatever the lock it is, unlocking step is same, right? Unlock of A. Similarly, see this situation. Initially some transaction is having write of A, after that read of A. So at this moment DBMS doesn't know that this transaction is going to read. Even T2 itself doesn't know that it is going to do read. Then initially your DBMS will try to achieve exclusive lock on A. Then slowly when time comes, so your transaction or your DBMS will realize that there is a read operation. So it is, definitely, I mean, so it, for that you just require shared lock, right? You don't really require exclusive lock. If you can downgrade your lock, then what can we do is other readers can come and join you. That is the flexibility, right? So if you keep exclusive lock and if you continue your process, other readers cannot hold the lock, right? So that's why we will go to downgradation, that is exclusive to shared. So this is not acquiring the new lock, but updating it. So but we are downgrading it, right? Not upgrade, just we are updating it to downgradation. So exclusive lock of A will become shared lock of A. After that, once your work is done, we can release it. This is a story of upgradation and downgradation. When you have read followed by write, usually go for first shared lock, after that upgrade it. And whenever you have exclusive lock, then when you have write followed by read, first go for exclusive lock, later you reduce it to shared lock. So such mechanism also we can implement. Think about it, like I don't teach the data structure part. You can take the necessary precautions and steps to do this thing, right? It's not a big deal. From now onwards we deal in high level. So I already explained you low level, like how this locking mechanism will be implemented. Now from now onwards only we see how we keep shared and exclusive. That's it. We don't go to the database variables and data structures and we make marking it the counter and marking available to 1, everything. We don't do that because it makes your discussions clumsy. Understand? So we only discuss like this.